So please welcome from Logix, Vinay Mehta.
Thanks for that intro, Tom. Can you hear me all right?
Yes.
Okay, great. So my name is Vinay, and I'm the Inference Technical Marketing Manager, as Tom mentioned, from Logix, where we're developing the X1 Inference Acceleration chip. Today, I'll be talking about accelerator evaluation on some real edge applications that we've seen coming from our customers. To give you a quick overview of what my talk will encompass today, I'll spend a little time at the top talking about the edge market as a whole and how we see kind of some of the different applications that are in the market space. Next off, we'll be talking a bit about some of the requirements that our customers have and what their both physical and software requirements are, before spending a little bit of time characterizing the different kind of workloads that come in. There's been a lot of good work from MLPerf, but sort of we want to lay out how we see all these different workloads and models as they apply to our chip. Finally, we'll spend a little bit of time talking about streaming and throughput, and how effective latency differs from the maximum throughput that you can actually achieve. And then we'll get into the benchmarks that our chip is able to perform. And then finally, I'll spend a little bit of time talking about the different ways that our chip handles convolutional memory access patterns, which is sort of the secret sauce, but the key to why we're able to achieve such high utilization across our multiply and accumulate units. So to put this all into context, I'll be talking primarily about the InferX X1 Inference Accelerator chip, which we have recently taped out. The chip itself consists of 4,000 multiply and accumulate arrays, and as I mentioned, they are held together by our patented eFlex technology, which you can kind of see up here. The reason we're able to achieve such high utilization is because we have the flexibility that the eFlex and XFlex interconnect provides. And at max power consumption, we see in our models an estimated 13.5 watts. However, that's, like I mentioned, max. During real world usage across these models, it's actually substantially lower, but we wanted to provide a kind of worst case scenario for when you design a system around the XFlex, around the X1. And I just one more thing I want to mention is that we will have samples beginning in Q3 as well as an evaluation PCI card. So as we see the edge market, there's a wide range of applications ranging from very complicated tasks like CCTVs with object detection and driver monitoring and ADAS systems, all the way down to some tasks that require simpler, more regular models which don't have as deep feature maps and also which perhaps aren't as deep. Some of these models we kind of have categorized as learned DSP, where neural networks, convolutional neural networks, are supplanting some of the applications previously done by hand-tuned DSP algorithms. Instead, you see convolutional neural nets replacing them, where they're kind of trained or learned, where the parameters are learned across a data set. Regardless of the complexity of the model, however, and the application, in the edge we see that there's this shared need for batch equals one, or streaming, low latency applications, and they tend to operate on a very large input size, usually directly coming straight from the sensor. So with these kind of core functional requirements in mind, we designed our X1 to handle, to perform optimized at low batch sizes, as well as on our memory hierarchy to operate well on large input sizes. So when a customer comes and evaluates our chip, the first thing we want to provide for them is really a representative workload. We try as much as possible to benchmark on the actual model that our customer intends to deploy, but in lieu of that, if that's not possible, we try to choose a model that's most like the model that they're running, and I'll get into that in a sec when I talk about characterizing different workloads. The next thing is, I think MLPerf has done a really good job with standardizing benchmarks, but there's still a little bit of a tendency to be unclear with the metrics, and as I'll kind of get into a little bit later, there's some confusion. There's a way for the customer to get a little confused when it comes to understanding, will this hardware actually be able to do what it is I want it to do? And most of this confusion really comes from understanding the difference between latency and achieved throughput. And then finally, when a customer comes to us, they really want to see how their how our hardware fits into their stack. And usually this goes beyond just how fast can you run our model. There are other factors that they have to consider. And so as an example of what I mean by that, our die and package as a whole is 21 by 21 millimeters. So just from that standpoint, being able to fit into smaller places enables a whole range of applications that otherwise wouldn't be possible. When you look at some of our competitors, kind of how we stack up against them, we are substantially smaller, and that comes with both the physical kind of benefits, but also our chip tends to be a lot cheaper than something like a NVIDIA NX or a Tesla T4. So the evaluation process really goes beyond just looking at performance. So when I was talking about choosing the right benchmark, the industry standard right now is and continues to be ResNet 224, batch size 1, at int8, FP16, take your pick. But we found that one model isn't really a good proxy for how other convolutional neural nets will perform on our hardware. And no one is really running just a stock ResNet 224 image classifier. So while that is a useful data point in isolation, it doesn't really tell the full story. And when you look at models, different models, even just different image classifying or object detection models like you see on the left graph here, you see that the arithmetic intensity can vary dramatically across models that are ostensibly doing the exact same workload. So we've chosen to, we've really heard a lot of customers coming to us and asking about YOLO v3. It's a very fast, fairly accurate object detector, and it just so happens that the darknet backbone that YOLO v3 is based around has a very high arithmetic intensity relative to some other models. On the right, you kind of see how this arithmetic intensity and also how the memory bottlenecks can shift, even given the same model, but just increasing the size of the input. So as your input size increases from, let's say, 224 up to 2 megapixels, or 1440 by 1440, the bottleneck shifts from being the total weights that you need to hold in memory at one time for a given layer, or the total weights you're going to hold for the entire model in memory, towards being the intermediate activations that you have to hold. That's what this green line shows, that as your weights increase in size, as your input increases in size, your bottleneck shifts from being the model itself to being the intermediate calculations that are computed by the model. And so when designing a piece of hardware and designing for a specific system, you really have to look at the workload itself in order to understand how the hardware is going to be able to perform. So next up, I mentioned a little bit about how there's the opportunity for a customer to get confused when they look at some benchmark numbers. And so to give you an example, we ran YOLO v3 at 2 megapixels, which is our kind of North Star, on the NVIDIA Jetson NX. And we were able to achieve, across the different compute units, the values you see here. The problem is when NVIDIA reports these numbers, they end up summing across the total frames per second. And this gives you a performance benchmark or a performance metric that really assumes that you're operating on all of the data at one time. It assumes that you can operate across all the images and that they're all available to you in a pool, so that you can perform inference in this kind of pattern where one processing element will operate until completion and then start on another image, whichever image is ready at that time. And all the processing elements sort of operate independently. The problem here is that you end up with, well, I'll get to what actually the problem means. But the first kind of thing to point out is that this 17.3 that you see, it might mislead customers in a way to think that they can run a sensor at, let's say, a 15 frames per second sensor. But if you actually map out on this sort of timing diagram and look at what a 15 frames per second sensor looks like when it's actually mapped onto a system like this, you find that for every given frame as it comes in at 15 frames per second, or every 67 milliseconds, you get a non-ordered output. What I mean by that is when an image comes in, it's not necessarily guaranteed to come out before an image that came in later than it. So for a real-time edge system, this doesn't this becomes a very confusing task for you to be able to schedule and handle. And so instead of putting in an image and getting that same image out 67 milliseconds later or some set amount of milliseconds later, you might get data back in a non-ordered fashion. So what you really have to look at when you're looking at a system with multiple compute elements is the fastest single processing element, which in this case turns out to be the GPU itself. What these benchmarks sort of don't tell you and don't show you if you were to just look at the sum of all of these is the fact that you can't use all the resources available on a piece of hardware for a single inference. You have to split it up. And when you split up inference across multiple resources, you're not really able to schedule all of them to terminate in the same way. And so what we really end up caring about in the edge world, kind of tying this back to edge data streams, is that you want your performance, the final performance number you really care about is your average or reported latency. What we're kind of talking about is effective latency. So to summarize, on the left you see the data stream that comes in from a data center, where all the data is available at a given time, and you can perform inferences in any order, and inferences can pop out, and image 5 can terminate before image 1 terminates, and you can stitch it all back together at the end. Whereas in the edge, you really want to be able to, you really get in data one at a time sequentially, and you expect it to come out sequentially as well, kind of first in, first out. And you want, so with that in mind, the X1 was really designed to operate well on single batch size edge streaming data coming in, and then very predictably giving you a response within the bounded latency that your performance is required by the model. So to get into some real world benchmarks here, we evaluated a couple customer models as well as some open source off-the-shelf models like YOLO V3 across the X1 as well as across the T4 and the NVIDIA NX. And you can see here that since there are two different processing elements on the NX, I've put both of them here. As you can see, in terms of latency, the X1 is able to outperform the NX, specifically the NX GPU and the NX DLA, and it's closer, in fact, to the performance of a T4. However, one thing to kind of notice here is that not all models, the pattern doesn't really, there's no one pattern across all the models. Since one model isn't really a proxy, it won't tell you exactly how another model is going to perform. So while there is some correlation between, let's say, two models of the same input size, two of our customer models, for example, we see where the NX is able to, not even able to run that model on the DLA at all, whereas the X1 is able to outperform the T4. And I'll get into this in a moment and how it kind of demonstrates how flexible and how adaptable our architecture is. But this picture doesn't really tell the whole story. What's kind of missing from this image is how power and cost factors into this as well. Since a customer doesn't come to us just asking for performance, they really care about the whole system picture. And so to that end, if you take a look at performance with a view towards die size, which is a proxy for cost in this case, we really see that the X1 not only outperforms, but significantly outperforms both the NX and the T4. And so in that use case in that first case again of the customer model, which had these operators which don't run on the DLA, we can really see that the X1's value proposition is very clear. And even across some other models like the open source models like YOLO V3, the X1 is able to achieve significantly superior performance relative to the price or the die size that it is. We also believe that this shows the inherent efficiency of the X1 in terms of performing inference. So one of the reasons why we were able to achieve such high performance relative to our die size, it comes down to the flexibility that we are able to rewire or reconfigure the underlying hardware resources given a specific convolutional kernel. So in this kind of toy example that you see here, in like a standard convolution, we end up taking a 3D activation space of height, width, and depth, as long as with depth being the different channels here, and in memory or across kind of the NOC as it comes in, we have to take this 3D activation space and transform it into a 2D activation space, or maybe it's stored in the 2D activation space, and then gets put into a 1D linear space, which is where how we actually perform our multiply, accumulate dot products. This is sort of the final form and kind of where our 1D systolic architecture is. So that's where how the data eventually needs to gets transposed. So at every step from every dimensionality step, there's room for optimizations. There's room for design, basically, where we can reorder the data or pack the data in a certain way or make decisions such that the efficiency of the underlying hardware is improved. So this kind of demonstration I've given here doesn't necessarily need to be in channel height width orientation. We could find that actually height width channel is a superior way to transpose the data, but that's kind of a toy example. And then eventually, after you do that multiplication, you end up with a single pixel or a single value in an output channel. And the process begins again, where you slide over the window. And even here, there's another room for optimization. Since you're operating on the same data, again, you don't have to change that data out. Or you can selectively change out the data or reuse that data or pack that data in place of the data that's been changed out already, which I tried to show here. So this kind of goes to show that there's a lot of room for there's a lot of room for optimizations, primarily in how you pack the data and how you organize the data. And our hardware is pretty well suited or adapt for that task, since it incorporates a lot of flexible, since it incorporates our patented eFPGA technology directly onto the chip. So in the case of the Model X, which I demonstrated, the specific operation that was unable to be performed on the DLA and which wasn't being performed with a very high efficiency on the T4 and the GPU was this 3D convolution, where instead of looking across a single input space, this is channels, you're actually looking across multiple different images, the channels in multiple different images. So this operation, the memory access pattern of this operation is significantly more complicated than the example I showed before. But again, due to the flexibility of our architecture, we're able to take the logic, the embeddable logic that we have here in the eFlex as well as in the XFlex interconnect, and reorder the data in a way that when it arrives at the NMAXs, which are the actual multiply accumulate units, it's in an order which makes it very efficient to be processed upon. And then on top of that, once we order the data in the right way, we can organize the actual compute clusters in a way where they are most optimized to operate on these convolutional kernels. So for example, instead of operating, let's say, each NMAX cluster independently like that, we can link up different NMAX clusters to be longer or shorter, so that, as I mentioned, the convolutional kernel maps more efficiently onto the underlying architecture. And like I mentioned, this is the chip that I've been talking about, and I'm happy to take any questions.
But let's take the first question here from an attendee. Boy, it's kind of a long one. I'll read it. Data centers have multiple customers running independent graph workloads. Inference edge devices support multiple camera algorithms to detect multiple objects from multiple viewpoint sensors. How does software stack isolate traffic to shared resources in the multi-chip mesh so that one workload doesn't act as spoiler traffic to the other flow or be susceptible as a victim to these other flows? That's pretty convoluted. Do you understand that?
I don't think, I can't say that I do entirely, but I'm happy to sort of speculate a little bit. I think what Richard might be asking is, how do you keep these different sensors isolated and stop one from bringing down the entire system? I think that's what I'm kind of seeing here. I don't know if I fully understand what the question is asking, but Richard, if you want to provide a little more context, I'd be happy to try and tackle it. Oh, please stop.
No. Well, we can come back to that one later, I guess, if you think of. We got a few more questions to ask stacking up here. What is the minimum number of neurons that can be flexibly programmed?
So in our NMAX, in our X1, we have 4,096 different multiply accumulated units. So at any given time, we can perform, in any given clock cycle, we can perform 4,096. But 4,096 multiplies. That doesn't mean that we only fit that many or support that many neurons per layer, if that's what your question is, since you end up reusing the same weights for the entire layer. We can fit 4,096 for a given clock cycle, and then on the next clock cycle do a different set of layers, or a different set of weights. So the question, if I think I understand it, is how many neurons are you operating on any given time? 4,096, but how many neurons are you constrained to in a given layer? That's up to the software programmer, really.
Okay. Oh, and in regards to that previous question, he responded, yes, it's not deterministic.
Okay, so I think I understand this question a little better. So the X1 operates as a coprocessor, really. It's controlled by a host usually, and that schedules some of this traffic for you. So if there's sensor data coming in at a non-deterministic rate, then we have to schedule that by the host.
Yeah, he follows up by saying during portions of the compute, there will be ebbs and flows and surges and conflicting use of intermediate shared memory banks or NOC or SerDes links.
So in this kind of example that we've given here, we're assuming that we're operating on a single camera stream with a single model. If we're operating on the same model with multiple camera streams, again, changing out the input is kind of a high-level scheduling task. Since you're only operating on a batch size of one on a single frame at a time, what you feed in will terminate before something new is able to start.
Right. Okay. Another question. Does the X1 do the data packing for convolution using the on-chip FPGA?
Yeah. So that is one of the functions of the on-chip FPGA is to order the data, like I mentioned. The on-chip FPGA also handles some of the operators that aren't decomposable into multiply and accumulate units. So some of your rectified linear and activation layers, stuff that doesn't map well onto the 1D systolic architecture. And it's a combination of the eFPGA and also the interconnect, the N-links in between the different NMAX clusters, which does this data reordering. What is the area overhead of doing it in hardware? It depends operator to operator, but we're able to achieve, like I said, pretty complicated memory access patterns like 3D convolutions across a fairly wide set of window sizes and stride sizes. So.
Okay. Next question. Is data conversion from 3D to 1D done in hardware? What is the area overhead of doing it in hardware?
Oh, sorry, I thought that was the same question. Data conversion from 3D done in hardware, what is here? So like I kind of talked about just before, you're not actually operating on 3D data, you're just transposing what's already in your SRAM, which is in a 2D data, to a kind of index form in 1D, in a one-dimensional stream. So yes, we're able to access, we have multiple memories on our chip where we store the activations and then put it into a buffer where we then have more control over how we're able to pull data out of it, and then before finally loading it into our NMAX clusters. So in every step in the hardware, we're able to do one more or a few more steps of data reordering. So the overall impact in terms of hardware overhead is fairly is not negligible, but like I mentioned, we're able to do pretty complicated memory access patterns which keep up with the rate of throughput of the compute unit.
Okay. Next question. Does your throughput area metric use the entire Xavier die area or area of the GPU DLA block?
That's a good question. So right now I was just using the area throughput, the area available to us on the of the entire SoC. I didn't have a die shot where I was able to estimate the GPU or DLA, but a more representative kind of number we could achieve by just using the GPU or just using the DLA. But the Xavier, the point that I was trying to highlight there is that the Xavier NX also has a lot of area on its SoC dedicated to functions that that we don't have dedicated to it, that we might not need for the task of just performing inference.
Okay. Another question. How would tensor sparsity be mitigated?
How would tensor sparsity be mitigated? So model compression and activation compression, if that's kind of a similar, is something we're looking into right now. Again, the kind of flexibility of our eFPGA should allow us to handle some of these kind of sparse cases dynamically. But as it is, we take the model as it's given to us without modifying it from what the customer has given to us and run it as is. So we don't make any sort of optimization changes in the hardware. That's not to say that you can't perform optimizations kind of in the compile stage or the kind of optimization stage prior to compiling it down to a binary that runs on the hardware.
Okay. We have a comment from Richard, who asked the question about the data centers. He said, "Thank you. These use cases require omniscient scheduling, and I have trouble scaling to very large systems."
Well, Richard, we're really talking not as much about the data center here. We're talking about some edge applications where you're only looking at a few camera streams at a time. But we will have an X1 configuration with multiple X1s on a single chip, and that should be able to, based on our models, we are able to scale up to multiple streams fairly efficiently.
Okay.
So I'll be hosting a breakout session at 12:10 along with some of my colleagues, and we'd be happy to dive deeper into some of these engineering questions at that time.
Yeah, that'd be a good time to do it during the breakout.
Yeah.
And that just about wraps up our 10-minute Q&A period here. So thank you very much. It's a good presentation and good answers.
Thanks, Tom. Appreciate it.
Okay.